All right, we're back. This is Calc C Notes 10, page 1. We're finally talking about Taylor series for real instead of just Taylor polynomials. Although when I think back to all the videos that we've made, I've probably referred to Taylor series like 100 times at least, because I like to jump the gun. And also we already knew about them, right? Because we knew we could just continue forever. And once we introduced the idea of continuing forever, it became pretty apparent that a Taylor polynomial could be a Taylor series. And so we already know a lot about them. So in particular, we know that a Taylor series is a power series and that it is a power series with a very, very specific coefficient. And the coefficient is this, the nth derivative evaluated at a, that's hard to say, divided by n factorial. So that's going to be our Taylor series. And you got to remember it, right? So it's nth derivative at a, x minus a to the n over n factorial. That's your nth term. And we're going to use that in a couple of ways. In particular, you'll use that. I feel like I'm saying in particular a lot, but that's probably okay. So you'll use that to figure out the nth derivative at a. Like given a polynomial, you can actually figure out the nth derivative, a Taylor polynomial or a series. You can figure out the nth derivative at a particular, a particular derivative. Well, I mean, it's got to be at a. I don't even know what I'm saying. You can figure out the nth derivative at a. That's what I'm trying to say. All right, let's write down summations and the first few terms of the essential Taylor series. So these are the most important. So sine is an odd function. So it's going to be only odds. And what do odds look like? 2n plus 1. And then 2n plus 1 in parentheses, factorial, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. Goes forever. Cosine is an even function. 1 minus x squared. Okay, I don't know why I started with this. Plus x to the 4th over 4 factorial minus dot, dot, dot. All of this is from 0 to infinity. Negative 1 to the n. X to the 2n. Quantity 2n factorial. Okay, so both of those are good for all values of x. We know how to figure that out. That's the interval of convergence. We use the ratio test. You're actually going to get, the limit will just be 0, which is less than 1 for all values of x. So it converges for all x. E to the x, 1 plus x plus x squared over 2 factorial. I don't know why I'm still going. I guess because the factorial is kind of like show up a little later. This is going to be just x to the n over n factorial. Also good for all x. You can do the ratio test. You're going to get that rho is equal to 0, which is less than 1 rho. Because remember, rho is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So we get this valid for all x. And then here, 1 plus x. Sometimes I have a problem or a tough time remembering that this one looks like this because it's so weird. This is our geometric, and this one is restricted because r has to be less than 1, the absolute value of r, less than 1. So these we have to know. You're going to use them to build tons of series. I hopefully have mentioned this before. The denominators, the factorials and the denominators are like the key to figuring out when you're dealing with a series, like what function does it converge to? Look at the denominators, look at the factorials and the denominators and work off of that, because once you have that down, you can kind of like go with it. All right, let's see. Compositions and power series. We're going to make new functions out of old functions that are make a new series out of an old series. So let's see if we can do that. So I'm going to start off with, what are we trying to do? Write this. First 4 terms, general term. For a neat comparison, graph the first few terms of your series in the function. Okay. I'm going to write this not in summation form, although summation form isn't that bad. But let's start with how we like to build these. So I'm going to say, I'm going to focus it on cosine. I'm just going to write cosine of u, right? Cosine of u, 1 plus u squared over 2 factorial. Oh my God, it's not that, it's minus. Minus plus u, like how could it be plus? Like cosine, very close to the origin, basically looks like a quadratic that opens down. And if you just take the first two terms, it's a quadratic that opens down. Like you can't really mess. Oh my God, why did I write 2? Focus. Am I just not focused? Let's keep going. U to the 6th over 6 factorial. General term, -1 to the n, u to the 2n, quantity 2n factorial plus dot dot dot. Okay, so now we use this to get cosine of 2x. And cosine of 2x is going to be 1. And then I'm gonna do the is it called expanding? Distributing? I'm not sure what it's called. I think I'm distributing. Didn't really seem right to call it distributing, but that's where we find ourselves. 6 factorial plus dot 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 plus -1 to the n, 2 to the 2n, x to the 2n. Remember, we want to pull everything apart so we have each potential base has its own exponent plus dot dot dot. All right, now we're going to take this and multiply by x. So x times cosine of 2x. So I refer to this as building a series. So we're going to build it a piece at a time, multiply everything you see by x. That's how the distributed property works. So this is x, 2 squared x cubed now over 2 factorial, 2 to the 4th x to the 5th over 4 factorial, and then 2 to the 6th x to the. So, I mean, take it from me because I've been doing this a long time, pretty confident, not like 100% confident in everything I do, but you get better at working with series. And like, you're gonna have moments where you doubt yourself because series are just weird, right? But we have a lot of things at our disposal. Like if we can graph, we should just try to graph it and see what happens. So I'm gonna write this as a summation. So this actually a little bit easier, right? Because cosine of u, based on what we know, would be -1 to the n, u to the 2n over 2n factorial. So don't be afraid to do this either. Cosine of 2x. Gotta write stupid summation all the time. So it's going to be 2 to the 2n, x to the 2n over 2n factorial. And so if we multiply through by x and use our properties, we're going to get, so I can bring that x in, and then it'll be -1 to the n, 2 to the 2n, x to the 2n plus 1, because x to the 2n times x to the first, you add the exponents, 2n factorial. Just like that. Like it's not bad. It's intimidating at first because like, so I think the most intimidating part is realizing like you don't need to make a table of derivatives to do this problem. And on the AP exam and in AP calculus in general, like you're very seldom asked to actually do that process. It's more like, do you know the series you're supposed to know? Do you know how to manipulate those? And that's what we just did. It's not like start from scratch and invent the wheel. Like that's not really what you do. I said I was going to graph that, but I'm not going to graph that because you know how to graph. And also I want to finish this page in this video. So you should graph that. Graph a couple of them. I mean, maybe just like graph both sides of this. Just kind of stop there and see. You'll see it matches up, hopefully, if we got it right, which I'm pretty sure we did. All right, this next one's going to be, it's a little weird, right? So first of all, x cannot be 0 for sure. Because if x is 0, you're trying to divide by 0, that's no good. X also can't be 1 or -1, but that's going to kind of like take care of itself. So I am making a note of this to begin with because I think that's going to stay super relevant. So what we want to do is same approach. So I look through here and I try to find what I can write a series for. Well, this I think I can write a series for 1 over 1 minus x to the 4th. So I'm going to do that. So I'm going to write my series for this. So 1 over, okay, so I'm already breaking my own rules. 1 over 1 minus u is going to be 1 plus u squared plus dot 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 plus u to the n plus dot dot dot. So 1 over 1 minus x to the fourth is going to be 1 plus x to the fourth plus x to the eighth plus, I'm going to do another, x to the 12th plus dot, 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 plus x to the 4n, because a power to a power, you multiply the exponents. So we get this. Now, what are we supposed to do to this? This is one of the neat things with series. I'm supposed to multiply this by 1 over x squared. There's actually two things I could do. I could take 1 over x squared out of both of these, and then it's 1 over 1 minus x to the fourth minus 1, and then multiply by 1 over x squared, which I could do, right? Just if I put a minus 1 here, this minus 1 will cancel with that, and we just have all these, and then divide by x squared. I'm doing it in a slightly different order, but that would have worked. So, you know, I want to, if you thought of doing that, that was a good thought and maybe better than what I'm doing. But this is what I'm doing. So I'm actually about to end up with not a power series. So this is weird. I'm multiplying everything by 1 over x squared. So I get 1 over x squared, x to the 6th, x to the 10th, x to the 4n minus 2. Right, because you divide, when you divide, you subtract the exponents. This is not a power series. It's not a power series because this is not going to have a positive exponent. That's not a power function. Power functions are x. Is that true? I think that's true. I mean, this is definitely not a power series because a power series you have to have all positive exponents. Now I'm not sure I know the definition of a power function. I think the exponent must have to be positive. I've never, like, what's confusing me is that I've used a power rule to find the derivative of 1 over x squared, but I'm pretty sure that's not a power function. So I'm going to look that up when I'm done with the video. Now I need to subtract 1 over x squared from both sides. And this, now we're going to be back to a power function. Power series. Power function, power series. Power series is made up of power functions, and a power series needs to have positive exponents. So I'm going to say power function must need positive exponents. Just, it has to. Okay, so we are subtracting 1 over x squared from both sides. There's only one over x squared to subtract, right? So it's going to come off of this. We're going to knock that off, and we'll just be left with x squared, x to the 6th, x to the 10th, plus x to the 4n minus 2, plus dot, dot, dot. This is it. I think this is our final answer to our thing, except, and this will happen with series a lot, two things. The first thing is that this is geometric, right? So at this point, we knew that we needed the absolute value of x to the fourth to be less than 1. So that's just the absolute value of x is less than 1. Absolute value of x is less than 1. And x can't be 0. So here, we get the absolute value of x is less than 1. X can't be 0. So it works. So what I'm going to do is sort of quickly try to show you on the calculator. Hopefully it's quickly. I don't know how long this is. I'm going to guess it's kind of long. I'm going to knock out the Taylor series. First, let's define the function. F of x is 1 over x squared, 1 minus x to the fourth, minus 1 over x squared. Okay. So I think the calculator just simplifies this. Yeah, it does. Okay. So even there, you lost 0, right? The calculator's warning you that the domain of the result might be bigger. It in fact is, because it knocked out that discontinuity at 0 by like algebraic manipulation. So that's a problem. Taylor, f of x, comma x. Let's go 10, what are you, 14, 18, 22. Okay, that's what that is. And then let's type in what we have. So we have from 0, we never did this. Oh, we did. What am I doing? So 22, 6. I'm doing some stuff here. I'm just gonna put in the nth term. This is what I'm trying to do. I'm trying to get it to spit out the exact same thing. No. Oh, because we knocked off the first term, so we're not starting at 1. We're not starting at 0, we're starting at 1, because we knocked off the first term, which was 1 over x squared. So we get this, and you can see that it does match, right? So I don't know, one of my videos, it like didn't say true, even though it was true, and that was unnerving. Anyway, we got it. So it's a really interesting problem. Making new series out of old series, like always easier than you think it's going to be. Don't immediately just start making. Don't just start making the table. Think like, do I already know a series that kind of applies? And use the series that applies. All right, I will be back in the next video to do more with these things because we already know a ton about them. And these notes mostly are just like reaffirming things that we already knew. So I'll be back. See you then.